Have you ever noticed how some apps you use, they just load instantly, maybe feel super fast, but sometimes the info seems, I don't know, a few seconds old?
Yeah, or the flip side.
Yeah.
An app that's always spot on, accurate, totally precise, but then occasionally it just hangs, makes you wait, or maybe even says unavailable right now.
Exactly. And you might think that's just random, like a glitch. But it's usually not. It's actually a fundamental design choice, really baked into how these online services work. And today, we're going to take a deep dive into the core idea behind it all, the CAP Theorem. It was introduced way back in 2000 by Eric Brewer.
That's right. And the CAP theorem, it's really a cornerstone concept in distributed computing. It highlights this foundational trade-off.
A trade-off.
Yeah, it essentially illustrates a general impossibility. You simply can't guarantee both what we call safety and liveness at the same time when you're dealing with unreliable distributed systems. It shapes pretty much the whole digital world we interact with.
Okay, so quite a big deal then. Our mission for this deep dive is to really unpack what these terms, consistency, availability, and partition tolerance, what they actually mean.
Right.
We'll dig into the theory a bit, why it's supposedly impossible. And then the really interesting part, I think, is how real-world systems actually deal with this.
Or practical strategies, yeah.
Exactly. How they navigate these challenges and maybe even peek at what the future looks like for these trade-offs. Think of this as your shortcut to understanding the design choices behind loads of services you use every single day.
Sounds good.
All right. So if this isn't just random chance, it must boil down to some core elements, right? What are these three pillars of C-key that designers are constantly wrestling with?
Absolutely. Let's break them down. First up is consistency.
Okay.
Now, in the CAP sense, consistency means that every single user, no matter where they are or which server they hit, sees the exact same data at the exact same moment.
Like a single source of truth.
Precisely.
Yeah.
Imagine you're trying to buy the very last ticket for a concert online.
Right, high stakes.
You need absolute certainty that when you click buy, that ticket is yours, and someone else isn't simultaneously buying it from a different server showing the same last ticket.
Okay, got it. So it's like everything happens in perfect sync, instantly, everywhere.
That's the ideal, yeah. As if there's just one central server managing everything. Now, it's worth noting that trivial services, like one that just returns the value of pi, don't really fall under CKP.
Makes sense.
And crucially, because achieving this perfect consistency is so hard with unreliable networks, many weakly consistent services have been developed. These are services that, relax that strict requirement. They prioritize maybe speed or availability over having perfectly synchronized data immediately.
Like my social media feed, maybe? Seeing a post from 60 seconds ago is usually fine.
Exactly. We'll definitely dig into those strategies later. So that's consistency.
Okay, pillar one, consistency. What's next?
Next up, we have availability. This one's maybe more intuitive. It's about always getting a response.
Every single time you ask for something.
Yep. Every request made to the service eventually gets some kind of response back. It doesn't necessarily have to be instantaneous, although faster is obviously better in practice. But for the theorem itself, even just requiring an eventual response is enough to cause problems when combined with the other factors. Of course, from a user's point of view, if a response takes forever,
it's basically useless. Might as well have not gotten one.
Right. But technically, availability in CAP just means a response will come back eventually.
Okay. Consistency, availability. What's the third one?
The third is partition tolerance. And this one's a bit different. It's not really a choice you make in your design. It's more a statement about the fundamental nature, the reality of the network you're running on.
So it's about the network itself being unreliable.
Exactly. It means communication between your servers isn't guaranteed. Messages can get delayed. Messages can get lost entirely. Servers can get split into groups or partitions that just cannot talk to each other for some period.
Like a major network hiccup, cutting off communication between different data centers, maybe?
Precisely that kind of scenario.
Yeah.
Or even just within a single data center if the network fabric has issues. It's the acknowledgement that the network layer isn't perfect.
Okay, so we've got C, consistency. Everyone sees the same data instantly. A, availability. You always get a response back eventually. And P, partition tolerance. The network is unreliable and can break.
You got it.
So with those three defined, the CAP theorem makes a pretty bold claim, doesn't it? You said it's an impossibility.
It does. The formal statement is something like, in a network subject to communication failures, it is impossible for any web service to implement an atomic read-write shared memory that guarantees a response to every request.
Whoa, okay. let's unpack that. Atomic read-write shared memory. That sounds like our single source of truth idea for consistency.
It is. It's the formal way of saying a system that behaves consistently, like that single server ideal.
And guarantees a response to every request sounds like availability.
That's the one.
And a network subject to communication failures is partition tolerance.
Exactly.
So basically, if your network can fail, P, you cannot simultaneously guarantee both perfect consistency, C, and perfect availability, A. You have to choose.
That is the absolute crux of it. You can pick 2 out of the 3, but you can't have all 3 when partitions are a possibility.
Can you give us a quick, proof or an example of why that is?
Sure, it's actually quite straightforward with a thought experiment. Imagine you've got just 2 servers, server A and server B. They both hold a copy of some important data, say the number of seats left on a flight. Let's say there are 10 seats.
Okay.
Now, a user connects to server A and books a seat. Server A updates its local copy, 9 seats left.
Right.
Server A then tries to tell server B, hey, update your count to 9. But, right at that moment, the network connection between them breaks. There's a partition.
Partition tolerance kicks in. Or rather, the lack of tolerance causes the partition.
Well, partition tolerance acknowledges this can happen. So server A knows there are 9 seats. Server B still thinks there are 10. They can't communicate.
Okay.
Now, another user connects, but this time they happen to connect to server B, and they ask how many seats are left. What does server B do?
Okay, options. If server B wants to guarantee consistency,
it knows its data might be stale because it can't reach server A to confirm. So to be perfectly consistent, it can't answer. It has to wait until the partition heals and it can sync up with A.
So it sacrifices availability. It doesn't respond.
Correct. But what if the system prioritizes availability?
And then server B has to respond, right? So it looks at its local data, sees 10, and tells the user 10 seats left.
It provides an answer, maintaining availability.
But it sacrifices consistency because the answer is wrong. There are actually only 9 seats.
Precisely. Server B is forced into a choice by the partition. It can be consistent or available, but not both. And here's a fascinating wrinkle. This situation can happen even if there isn't a true hard partition. If the messages between A and B are just delayed for long enough, server B might think there's a partition. It times out waiting for a response from A and is forced into the same dilemma. Wait indefinitely, sacrificing A, or respond with potentially stale data, sacrificing C.
Wow. So even just significant network lag can trigger this fundamental CIP trade-off.
It absolutely can.
Okay, that really clarifies the core conflict. But you mentioned earlier, this feels like part of a bigger picture, not just about C, A, and P specifically.
That's a great point. Yes, the CIP theorem is really a specific instance, a very famous one, of a much broader, more fundamental trade-off in all of distributed computing.
Which is?
The inherent tension, the impossibility, really, of simultaneously guaranteeing both safety and liveness properties in any system where components can fail or communication is unreliable.
Okay, new terms.
Yeah.
Safety and liveness. What do those mean in this context?
So think of safety properties as ensuring that nothing bad ever happens.
Like getting the wrong answer.
Exactly. Consistency, as we defined it for CAP, is a classic safety property. You want every response to be correct according to the system's rules. No incorrect data ever gets returned.
Okay, safety, nothing bad happens. What about liveness?
Liveness properties ensure that eventually something good happens.
Like getting an answer.
Precisely. Availability from TAP is a perfect example of a liveness property. Every request eventually receives a response. Something good getting a response eventually occurs.
Got it. Safety, correctness, liveness equals progress.
That's a good way to put it. And when we talk about unreliable systems, we mean systems where things can go wrong. CAP focuses specifically on network partitions as the source of unreliability.
Right.
But unreliability can also come from servers crashing, messages just getting lost for other reasons, timeouts, or even, malicious attacks trying to disrupt things.
So CAP is basically saying when network partitions, a type of unreliability, happen, you can't guarantee both safety, consistency, and liveness, availability.
You've nailed it. It's a specific illustration of that general safety liveness impossibility focused on partitions.
Was this safety versus liveness idea known before CAP?
Oh, yes, very much so. In fact, there's a landmark result from 1985 by Fisher, Lynch, and Patterson, often called the FLP impossibility result.
FLP.
Yeah, Fisher, Lynch, Patterson. They prove something quite profound. Achieving consensus, basically getting a group of distributed computers to agree on a single value, is impossible in a system where messages can take arbitrary amounts of time, asynchronous, if even just one single computer might crash fail.
Wow, impossible even with just one potential failure. Why?
Because consensus itself requires both safety properties, like everyone agrees on the same value agreement. And the value agreed upon was actually proposed by someone, validity, and aliveness property, namely that the process must eventually finish and decide on a value, termination.
So consensus needs both safety and liveness, and FLP showed you can't guarantee both if there's unreliability, even just one crash.
Exactly. Another powerful demonstration of that fundamental conflict. And actually, achieving atomic read-write consistency, like in CAP, is technically easier than achieving full consensus. So the fact that CAP shows atomic consistency is impossible under partitions also implies that consensus must be impossible under partitions too.
That makes sense. It all seems to point back to this core tension. So if we really can't have all three, consistency, availability, partition tolerance, how on earth do the systems we use every day actually function?
Right. That's the million-dollar question.
It feels like something has to give. Practitioners, the people building these systems, they must be consciously choosing to sacrifice something, right? Or maybe finding clever ways around it.
That's exactly it.
Yeah.
Since the network is unreliable, you have to assume P, partition tolerance, is a reality you live with. Designers are forced to make a strategic choice. Do they prioritize consistency, or do they prioritize availability? Or, as you hinted, do they get clever and segment things?
Okay, let's walk through those strategies. What does it look like when a system decides to guarantee consistency, even if it means sacrificing availability sometimes?
This approach is often called best effort availability. The absolute priority is correctness, is consistency. The service must return the right answer, according to its specification, no matter what's happening with the network.
So if there's a partition and it can't be sure it has the right answer?
It stops responding. It becomes unavailable for that request, or maybe entirely, until it can reestablish communication and guarantee correctness again. Now, while it guarantees consistency, it still tries its best to be available and responsive when the network is healthy.
Where would this make sense? Maybe where the network is usually pretty solid.
Exactly. This is often suitable for systems running within a single, well-managed data center where partitions are hopefully quite rare.
Got an example.
A classic one is Google's Chubby Lock service. Chubby is used internally at Google for really critical coordination tasks, managing metadata for distributed file systems, handling coarse-grained locking between services, even acting as a highly consistent naming service, sort of like an internal DNS replacement.
So, super important stuff that has to be right.
Absolutely. Chubby provides very strong consistency guarantees. It achieves this using a design with a primary server and backups, and they all keep their logs synchronized using a consensus algorithm called Paxos, which is related to that consensus problem we mentioned.
Paxos. Heard of that.
Because it needs consensus, if Chubby servers get partitioned such that the primary can't talk to a majority of the servers, it deliberately makes itself unavailable. It chooses C over A during a partition.
But when the network is working, which is most of the time in a data center,
it offers very high availability and fast, consistent operations. So strong C, best effort A. Perfect for its use case within Google's infrastructure.
Okay, that makes sense. What about the other way around? Prioritizing availability, even if consistency sometimes suffers.
That's strategy 2. Best effort, consistency. Here, the design philosophy flips. Availability is king. Getting a response, and usually a fast response, is paramount.
Even if that response might be based on slightly stale data.
Correct. The system guarantees it will respond, but it only makes a best effort to ensure the data is perfectly consistent and up-to-date across all replicas. Consistency is often eventual, meaning the data will eventually become consistent everywhere, but there's no guarantee on when.
This sounds like it would be good for things spread out over the internet, where network delays and hiccups are much more common. Spot
on. This is very common for wide area distributed systems, and the absolute classic example is web caching.
Like content delivery networks, CDNs, Akamai, and Cloudflare and those guys?
Exactly like Akamai. They operate massive networks of cache servers deployed all around the globe, close to end users.
Right, so when I visit a website, I often get the images and stuff from a server nearby, making it load faster.
Precisely. This provides incredibly high availability and very low latency responses. But think about consistency. If the original website owner updates an image,
it takes time for that update to get out to all those thousands of cache servers worldwide.
Right. So for a period, you might see the old image, while someone else connecting to a different cache server might see the new one. Or maybe you see the new text, but the old image.
So definitely not strongly consistent, but usually for web browsing, that's perfectly fine. I'd rather the page load fast than wait minutes for perfect global synchronization.
That's the trade-off in action. For most web content, speed and availability are far more critical to the user experience than instantaneous consistency. So they choose A over C.
Okay, so we have systems choosing C, like Chubby, and systems choosing A, like Akamai. Are there approaches that try to, find a middle ground?
Yes, there absolutely are. This leads to a more nuanced strategy, sometimes called trading consistency for availability, or exploring the idea of continuous consistency.
Continuous consistency. Sounds intriguing.
The idea here is that consistency isn't always a binary all-or-nothing thing. Maybe you don't need perfect consistency, but eventual consistency is too loose. Maybe you can tolerate data being, say, 5 seconds out of date, but not 5 minutes.
So you can actually define and tune the level of acceptable staleness.
Exactly. Researchers like you and Vedat formalized this. They developed a theory in a toolkit called TACT, which stands for Tunable Availability and Consistency Trade-offs.
DTT, okay.
TACT allows applications to specify their desired level of consistency using metrics they called CONATs. CONATN could represent a time limit, data no older than 5 seconds, a version limit, no more than 2 versions behind, or maybe track-specific update sequences.
How would that work in practice?
Think about an airline reservation system. When a flight is mostly empty, maybe having the seat count be a minute or 2 out of date isn't a big deal. There's plenty of buffer. The system can prioritize availability and speed.
Right, low risk of overbooking.
But as that flight starts to fill up, getting close to the last few seats,
suddenly, consistency becomes critical. You absolutely cannot sell seat 15B twice.
Precisely. So a system using something like TACT could dynamically increase its consistency requirements as the number of available seats decreases. When seats are scarce, it demands much fresher, more accurate data, potentially becoming less available or slower if network issues prevent it from guaranteeing that higher consistency level.
So it adapts the CA trade-off based on the current state or risk.
Exactly. It's not strictly choosing C or A upfront, but rather navigating the spectrum between them. It might end up sacrificing both strong C and guaranteed A in some scenarios, but the payoff is significantly increased tolerance to network disruptions while still meeting the application's core needs.
That's pretty clever. Okay, so we've got C first, A first, and tunable trade-offs. You also mentioned segmentation.
Yes, and this is incredibly common in complex real-world systems. The idea is segmenting consistency and availability instead of applying one single CAP strategy to the entire system.
You break the system down into smaller pieces?
Exactly. You divide it into various subsystems or components, and each part makes its own CA trade-off based on its specific function and requirements.
So the system as a whole might look like it's making complex compromises, but really it's just different parts doing different, simpler things.
That's a great way to think about it. And this segmentation can happen along several different lines or dimensions.
Like what?
Well, one dimension is data partitioning. Different types of data within the same application might have vastly different needs.
Example.
Think of an online store, your shopping cart contents. Maybe high availability is key. If it occasionally shows an item you removed a second ago, it's annoying but not catastrophic. It can be eventually consistent.
Okay.
But your actual order history or the billing and payment processing records,
Those have to be strongly consistent. No room for error there.
absolutely. So the shopping cart subsystem might choose A over C, while the checkout billing subsystem chooses C over A. Same application, different data, different choices.
Makes sense. What other ways can they segment?
Another is operation partitioning. Different actions a user takes might have different requirements. Read operations are often easier to make highly available, maybe by reading from potentially slightly stale replicas.
Like just browsing products.
Right. But write operations like adding to the cart, placing the order, those might require stronger consistency and could potentially be slower or even fail during a partition. Yahoo's PNUTS system was designed with this kind of per record, per operation tuning in mind.
So reads are fast and available, writes are careful and consistent.
Often, yes. Then there's functional partitioning. This is about using entirely different specialized services for different jobs within a larger architecture.
Like microservices almost.
Kind of.
Yeah.
We already saw an example using something like Chubby for tasks needing strong consistency, like distributed locks.
While using something like DNS, which is known for being highly available, but only eventually consistent for service discovery or naming.
Exactly. You use the right tool with the right CAP characteristics for the right job.
Okay, data type, operation type, function. Any others?
A common one is user partitioning. You can divide your user base, often geographically, and optimize for consistency and availability within each group.
How does that work?
Think of Craigslist. They might have separate infrastructure, maybe distinct data centers, serving the East Coast versus the West Coast of the U.S.
So my posts and searches on the East Coast are handled primarily by East Coast servers.
Right. This means interactions within the East Coast region can be highly available and relatively consistent locally. There might be some delay or temporary inconsistency if you're trying to interact across regions during a network issue between them, but it optimizes the experience for the majority of users interacting locally.
Segmenting by location. Clever.
And one more. Hierarchical partitioning. You can structure applications or data in layers, often geographically again, maybe with different performance or consistency guarantees at different levels of the hierarchy. Perhaps data is strongly consistent at a regional level, but only eventually consistent globally. Availability might be better towards the leaves of the hierarchy, closer to users.
Wow, okay. So designers have quite a toolbox for dealing with CAP. See, choose A, tune the trade-off, or break the problem down by data, operation, function, user, or hierarchy.
That covered the main strategies, yeah. It shows how systems cope with that fundamental impossibility.
This deep dive really has, well, it's shown a light on how that CAP theorem isn't just theory. It forces these really practical, sometimes complex design choices. And these strategies show how systems manage to work to kind of do the impossible by being smart about what they sacrifice, where, and when.
Indeed. It's a constant balancing act, and it's not static either. These trade-offs and how we approach them are constantly evolving as the landscape changes.
How so? What new challenges are shifting things?
Well, one huge one is just scalability. Building systems that handle massive load. There's often an inherent tension between achieving very strong consistency and achieving massive scale. Protocols like Paxos, which give strong guarantees, can become bottlenecks when you try to apply them across thousands or millions of servers, even within a single data center sometimes.
So the drive for bigger scale pushes designers towards relaxing consistency.
It often does. Or it forces innovation in how consistency is managed at scale. Another area is tolerating attacks.
Security.
Yeah. The original CAP theorem mostly thinks about benign failures like network partitions or server crashes. But modern systems face deliberate attacks, denial of service flooding networks, malicious users trying to corrupt data. These require different kinds of thinking about availability and consistency guarantees under adversarial conditions. It's more complex than just a simple partition.
Right. The P in CAP might not fully capture a determined attacker.
Exactly. And a really big one now is the rise of mobile wireless networks.
Because phone connections are just inherently less reliable.
Massively so compared to wired data centers.
Yeah.
You have constant issues with signal loss, high and variable latency, devices moving between networks. It's like partition tolerance on steroids. So applications designed for mobile, maybe like location-based services like Foursquare back in the day, or modern equivalents focusing on geography, social check-ins, real-time updates from moving users, they face really unique versions of these CA trade-offs. User expectations might be different. The network behavior is definitely different. It makes the design choices even harder and more tailored to the specific mobile context.
So the fundamental tension remains, but the context, scale, security, mobility keeps changing the specific calculation designers have to make.
Precisely. The principles of CAP endure, but their application is always being reevaluated.
So wrapping up then, the next time you're using an app and it loads like lightning, but maybe the notification count is a second behind, or maybe you're using a banking app that's always perfectly in sync, but occasionally asks you to wait or retry.
You'll know what's likely going on under the hood.
Yeah, you'll know that behind that experience are designers wrestling with consistency, availability, and the realities of partition tolerance, making intricate choices to deliver that specific service for you. It's definitely not random. It's a constant, calculated balancing act.
Could have said it better myself.